And here is one more problem, perhaps also from IIT book. The problem statement is so that a beam of light successively reflected from three mutually perpendicular plane mirrors. Yeah, just look at a corner of your room and you will find these three mutually perpendicular planes. And the problem is that so that a beam of light successively reflected from three mutually perpendicular plane mirrors will change its direction to the exact opposite. Oh, after reflection. This is the so-called corner reflector, an ideal object for radars. So, this is the problem. And this is one of the most obvious problems and easiest amongst all. We can solve it in many ways. So let's solve it. And here is the first solution. And the first solution is simple. Let us choose the coordinate axis x, y, z. X, Y, Z, so that each axis is perpendicular to one of the mirrors. We have three planes and three perpendiculars in terms of x, y, and z axis. And let the unit vector E naught, which specifies the direction of the incident beam, and it's simply going to be written like this without any hesitation, and that is EXI cap, because it will have three components plus plus EZ k cap, and after reflection from the mirror which has a normal along x-axis, well, one of the mirrors will have normal along x-axis, and then the corresponding component of vector E will change its direction to the opposite, and the rest will remain unchanged, because the next is going to be after first reflection, whose normal is along the x-axis. This thing will become something like minus EXI cap plus EYJ cap plus EZK cap, because after reflection the normal component of the incident ray changes its sign to the opposite, and rest remain unchanged. Rest of the terms remain unchanged. And in the similar manner, when this ray will encounter the mirror which has a normal along y-axis, the normal component is going to be changed and rest will remain unchanged. And in the similar manner, when reflected from the mirror having normal along the z-axis, the thing is going to change as like this. And so after three successive reflection, this will become minus A naught. So this is a simple solution. But if you don't like the solution, you think no mathematics came in the picture, so you can solve it another way, like formula we earlier obtained from a reduced problem, that after reflection the unit vector along reflected ray can be written as E naught, that is unit vector along the incident ray minus twice unit vector E naught dot n multiplied by unit vector n. And so if the normals of the mirrors are in this case n1, n2 and n3, you can write the first reflected ray E1, the unit vector along the reflected ray from the mirror whose normal is n1, you can write it like E naught. E naught is the incident ray, unit vector along the incident ray, and E naught minus twice E naught dot n1, n1. And in the same manner you can write E2 equals E1, because E1 is now the incident ray, minus twice E1 dot n2 multiplied by unit vector n2, and E3, the third reflection, the unit vector becomes E3, and now the incident ray is E2, so you can write it as E2 minus twice so E2 dot n3 multiplied by unit vector n3. And adding, you can add separately the left and right side of these equalities, and you will finally get I have already got, so I don't need to get it again. E3 equals E naught minus twice E naught dot n1 plus E1 dot n2 unit vector n2 plus E2 dot n3 multiplied by unit vector n3, unlike this. And here E1 dot n2, both are unit vectors, and the angle between them is equal to 90 degree. And here that E1 dot n2 is equal to E naught dot n2, because both are scalar quantities, and E naught and n2 are also perpendicular, and so are E1 and n2, so both are equal to 0. So 0 can be equated to another 0, or you can also write here that E1 dot n1 equal to E1 dot n2 equal to E naught dot n3, and so you can also write these terms. E naught dot n3 will be equal to E1 dot n3, and that will be equal to E naught dot n3. You can write like this because all are zeros. So in this formula E3 can be written as E naught minus twice E naught dot n1 is here, plus E naught dot n2 plus E naught dot n3 multiplied by unit vector n3, and like this you can write here. And you can now say that the quantities in this parenthesis are directions cosines of the unit vector E naught with respect to the coordinates with the unit vector n1, n2 and n3. It means the quantity the in the square bracket is simply E naught. It is simply E naught. And that means the whole term is only E naught. That means E3 equals E naught minus twice E naught, and that is equal to minus E naught, and which is what we required to be proved, and it is solved again. So whatever method that you like, you can solve it. This is if you don't understand, this E3 was simply E naught minus twice E naught, then that N1 was simply if the incident ray makes an angle alpha, beta and gamma with the three perpendicular mirrors, and if it makes an angle alpha with the mirror whose normal is along N1, and if it makes angle beta with the mirror which makes an angle beta, and so you can write here cos alpha N1 plus cos beta N2 plus cos gamma N3, like this. And this was basically E naught cos alpha, E naught cos beta, E naught cos gamma N3, like this. And this is nothing but E naught x plus E naught y plus E naught z, like these terms. Not exactly, but like this. And so this whole vector is nothing but E naught vector. And so this is 2 E naught. Try to understand these things. These are simple vectors. Thank you very much for watching.